Welcome everyone to the week 6 tutorial session. I am Rati Ludani, your TA for Algebraic Combinatorics, and I am a research scholar at Indian Institute of Technology, Bombay, at Department of Mathematics. So today we'll discuss some sample questions related to week 6 lectures. So let's begin. Let f be a species of a structure such that fx is equal to minus log 1 minus x. Then what will be the number of f structures on 6? So I hope you have looked at the lectures. So okay, so basically f is a species so f is a species of a structure. So that means there's a structure on every u where u is the finite set. Is a finite set. So for example, a structure of permutations, like we just consider the permutation on n, that could be one structure. So basically f could be like, as an example, permutation structure. That means you consider the permutations. So u is a finite set. So basically, as it is written, cardinality does not depend on which. So it just depends on the cardinality of the set. So you can consider u to be some such kind of n. So basically, we can always think of in terms of subsets. Subsets are basically the numbers. So f. So you just consider the permutations of 1 to n. I'm just giving an example. So this defines a structure on every finite set. So you just consider the finite set and you take all the permutations from that set to itself. Okay. So is that clear? Okay. I hope. Am I audible, right?
Yes, ma'am.
Okay. So yeah, f is a species of structure such that it is given that fx. So fx is basically exponential generating function. So this is also these. So I can define everything. Fx and f tilde x is type exponential function. Sorry, type generating function. If I'm not wrong, we can see that actually. Yeah, type generating function or series. Yeah. So type generating series. And one more minute. Yeah, that's okay. So exponential generating series, I think, or maybe it does not matter, it's just the terminology. Okay, so and fx is from where it is coming. So if you have, for example, the cycle index series. So what is cycle index series? If you this is the notation for cycle index series. That is something summation. Okay, I'll copy paste.
N belongs to
Yeah,
N.
exactly. Yeah, yeah, thanks for saying. I'll just copy paste. Yeah. Okay, so this is the formula for cycle index series. Now from this you can always you can find out what is fx, which is just if you put x1 to be x, x2 to be 0, and everything to be 0, then you will just get n belongs to n, which is again, if you put everything here, you will just get identity, like only identity will, in the summation, you just take identity, then only you will get the fixed points. So because of that, you will just get cardinality of Fn. These are in lecture, so I'm not explaining properly. So yeah, this is the formula. And f tilde x will be zf x, x square, x cube. You just take this. Okay.
Ma'am, how to find the cardinality of Fn power F sigma?
Cardinality of
Fn
this
power
one.
F sigma.
Okay. So
Yes, ma'am.
yeah, these are the fixed points. So here, if you see, what is this? This is all those x belongs to fn, such that f sigma s is equal to s. So it fixes your s. Okay. Now what does that mean? S is itself a, so for example, if you are in permutation thing, so s itself is a permutation, because you are talking about fn, right? So this itself a permutation. Now you think of all the, so here you have uh, n to fn. Okay, this color I think not visible. So here you have f sigma, sorry, f sigma is a map from fn to fn. Okay. Now this is a bijection, right? So you have to find out all the f sigmas, sorry, all the all the elements in fn, such that fn goes to fn, like it fixes it. So if you take s, it maps to s itself. Okay. So and s itself is a permutation, it's not a set, it's not a element of set. So so you are saying the permutation goes to itself. Okay. That is something you have to calculate, so it's not that easy. So if you have seen in the lectures, like the calculations are really, you need to calculate properly. So yeah, so for example, in this situation, what is happening, if you want to calculate for, so you are saying x 0 0 0 0, so this is your x raised to power sigma 1, these are, so sigmas are basically, sigma belongs to Sn, sigma 1 is like a number of cycles which have length 1.
Types.
Yeah, cycle type, you are just looking at the cycle type of sigma. So this is something, the cardinality of one cycles, cardinality of two cycles in your sigma. Okay. Now you have to calculate this value. So here if you see, this value, this x sigma 1 0 sigma 2 is equal to 0 unless sigma is equal to identity. What does that mean? You have only one cycles, because if you have any two cycle or three cycle, then 0 raised to power will be something, then it will make this coefficient, this term to be 0. So you want sigma 2 sigma 3 and everything to be 0. So that means you have to consider only those cycles which have only one length cycles. Sorry, you have to consider all those permutation which have only one cycles. That is just identity. You know that you have just one cycle. You are saying every element is just mapping to itself, right? So so that means you have to just find out for this cycle, for this permutation. So this permutation says sigma belongs to Sn, such that Fn raised to power F sigma. Right. Now what does now what you are saying in this cycle, in this S, so this is your S, what has been asked, which S, like, how shall I say, okay, sorry. So you are saying all those S belongs to Fn, such that F sigma S is equal to S. So here in this case, F sigma, so okay, this is mm, what shall I say? So basically, F sigma, you are taking F sigma, and sigma is your identity here. Okay, now you are trying to calculate F identity. F identity is Fn to Fn, and what does that do? That so basically, if you see, what shall I write? So I want to conclude that all the s all the s is actually,
Elements,
yeah, uh,
all the elements have the unique image.
yeah, there is one possibility only, and like everything mapping to itself, that I want to say that actually this is happening because this is identity. uh,
Mm.
you are considering not s, yeah, this is not s. Yeah, so basically what is happening, yeah, now I can say, so you have fn to fn. Okay, now you have any permutation. So let's say the confusion is like there are so I should not say permutation because it could be any set. So that was just an example. So you take any any element of fn, that is, let's say s, then it is mapping to sigma of s. If you see the like how sigma is acting on it. So sigma of s is basically what? Sigma is identity, so it is going to be s always. So all the elements will be fixed. So that
Yes, ma'am.
is, yeah, so cardinality of this will be equal to cardinality of fn, like all the elements, all the s will map to itself, so full set fn will be there. So is that okay?
Yes, ma'am.
Okay. So yeah, this is the way. This is a way to calculate, and like so basically you need to think. This happens with functors. Functors is a class of things. So you are basically considering class of all the permutations, and and thinking of permutation is mapping to some permutation. So you are going one step ahead of it. So that's why it makes so that way sometimes it becomes confusing. Okay, let's come back to our question. So f tilde x will be this is something using Burnside lemma. Again, I'm just writing the formula directly because it's there in the notes. So orbits, you consider the orbits and these orbits, and here you will get this. So these are two formulas, right? So here this represents in, okay, so here what is happening, fn x raised to power n factorial. Now here this value, this says what are all f structures you can apply on square bracket n. So this is the number of, or maybe I'll count of f structures on n. Okay, so how many f structures you can impose on square bracket n? Okay, like permutations. Now on a square bracket n, how many permutations you can put? Okay, so
Number of permutation.
yeah, so it depends, like how, where we are looking, and so it's just one example. If you take
Ma'am,
f to
so
be the
number of permutation means we have one definition, na? N factorial divided by summation I power ai into
no,
a
this is
factorial.
not an example. Like this is the general. Here we f could be anything. It could be linear order. It could be anything. So
Okay,
here
ma'am. If
here
FB permutations means that time we can.
yeah, it is not related to permutation. I'm just giving an example side by side so
Okay,
that you
ma'am.
can understand, but this is in general, like f structure could be anything. You can
Okay.
define it to be partitions of, and you can define it to be linear order on n, like x1 to xn. So it could be anything.
Ma'am.
If you have seen the lectures, there are many examples. Okay,
Yes, ma'am.
yeah.
Ma'am.
So yeah, this is the count of f structures on n, and here this gives the count of equivalence classes or isomorphism class, isomorphism classes of F structures on N. Here you are considering isomorphism classes. Okay, so that is so this is from the lectures I've just written. One more thing. So what is Sn orbit? So you are just taking the orbits of Fn with respect to Sn. So it's like if you, the notation says, so this is up. You just take all the GUs where U belongs to U. So similarly, you have Sn, you take any F, any element of this. So you are considering all the equivalence classes, all the isomorphism classes you have. Okay, so these are the orbits, so number of orbits in that sense. Okay, so this is regarding the formula. So now let's come back to our question. Yeah. So what has been asked, like if fx is equal, sorry, yeah, if fx is equal to minus log 1 minus x, then what will happen? So that is the question. So then what will be the number of f structures on 6? So you are asking for 6 it has been asked. So how many f structures you can impose, you can have. Okay, so fx is now from the formula you know that fx is equal to this. If fx is equal to this summation, then the coefficient of x raised to power n by n factorial will give the f structure on n, right? So now what you can do, you just try to expand it out. So log 1 minus x is what? Minus x square by 2. If I'm not wrong, this is the expansion, right? So the formula is log 1 plus x is what? 1 plus x is x minus x square by 2 plus x cube by 3 minus x raised to power 4 by 4 and so on. So when you put minus x here, you will get minus x. Here the square is there, so it won't bother. Here you will get minus and so on. Yeah. So this will be just all minus. So from this step, yeah. So from this step, now you know this is equal to x plus x square by 2 plus x cube by 3 plus x raised to power 4 by 4 up to and so on. Okay. Now you need to what you need to do, now you need to find out the coefficient of x raised to power n by n factorial. So how can you do that? You can just write the equality and you will be done. I'm just removing the formula. Yeah. So coefficient or so here what will be the sixth x raised to power 6 term? You have x raised to power 5 by 5, you have x raised to power 6 by 6 plus up to and so on, right? Now you have x raised to power 6 by 6. You need to compare with fn. Oh, this should be square bracket. Yeah, this is not something, because we are not saying this is some function or something. This is the notation. All the f structures on a square bracket n. This by n factorial x raised to power 6. So from this, what can you say? 1 by 6 should be equal to fn by so now n, you know n is your 6 because n is this power, right? So this is 6 and you have 6 factorial. 1 by 6 is equal to f6 by 6 factorial, right? So you will get f6 to be 5 factorial. Is that okay? So that is like 5.
Yes, ma'am.
Great. So this should be 4 into 24 into 5. That should be 120. Yeah, so this will give the value. So whenever it has been asked how many f structures you can have, you'll just calculate using the exponential generating series of function. I'm not sure what it is, the name. Yeah, that's okay. Okay, now okay, I hope this is clear. Then let's move to the next question. Now what will happen if, now again you have a species of structures, combinatorial species. Now and f tilde x has been given. So that is, this is z f x comma x square. You just take the cycle index series and yeah, you just put x1 to be x, x2 to be x square, and up to and so on. Then you will get your type yeah, type generating series, right? So now what has been asked, count the number of isomorphism classes of f on 6. So how will you do that? Now you have to calculate the isomorphism classes of f structures on 6. Yeah. A recipe is already there. We have discussed in first question. I can just go there. Can you point out?
Second one. Second one.
Yeah.
F for
Yes.
cardinality of Sn,
Hmm.
Fn, Xn.
Yeah. So you just take these are
Fn
the.
of X is equal to
Yeah, exactly. You just need to expand your function. So whatever the type generating function being given, so type generating series, then you just expand it out and compare the coefficients. Whenever you do that, you can get count of isomorphism classes of f structures on n, which has been asked, right? So you can consider so this need to be remembered, like whenever type generating function is given, then you can consider the isomorphism classes, and if exponential generating function uh, been given, then you can count the directly the f structures on n. You cannot calculate isomorphism classes out of it just by looking at the form, looking at exponential generating function. If there is any extra condition, then you can certainly try to do that, right? Because powers has been mixed up. Now how will you calculate, that is main thing, right? Okay. So here, and always remember the number of isomorphism classes of f structures on 6 will be always be less than or equal to number of f structures on n, because these are the isomorphism classes, right? And that is the whole count. So let's see what is happening here. So f is the species of structures and f tilde x is given to be 1 by 1 minus x. Now let's see what is happening. So what you need to do, you need to again expand it out. So what will you get? So this 1 by 1 minus x can be expanded like this, right? This is the formula. You have seen this in the formal power series lectures also. Yeah. So inverse of 1 minus x. So f tilde x is equal to this. Now, so again you need to compare. So number of, or maybe, yeah. So now there is no nothing anything, there is no like n factorial thing or anything here which can be which can confuse you. So you just basically take the coefficient of x raised to power 6, right? So take coefficient of x raised to power 6 will be what? Your number of isomorphism classes of F structures on 6, right? So coefficient of x raised to power 6 is what? This is equal to 1, so the answer should be 1. So yeah, nothing to be done now. Is that clear?
Yes, ma'am.
Yeah, and there is one correction here. If like it is typo basically. uh, Here, like this is not divided by 1 by n factorial. This is okay, but when you write here, you can just remove n factorial from here. So this might confuse you. So this is the same thing, just generalization. So you will not get n factorial because you are using Burnside lemma. So the order, so basically the fixed points, yeah, so stabilizer into the cardinality will become orbits, number of orbits. So from there you will be like n factorial into this value, sorry, n factorial into this value will become this. Okay, so this is the use of one side here, and so in general you will not get n factorial. So okay, is that clear?
Yes, ma'am.
Okay. Okay, let's move to the next question then. Let F be the species of structures with ZF x1, x2 up to and so on. Is the product n greater than or equal to 1, 1 by 1 minus xn. So now again, F is the species of structures and ZF. Now the cycle index series has been given, that is equal to product and greater than or equal to 1, 1 by 1 minus xn. Now find the number of isomorphism classes of F structures on 3. How can you proceed? How will you proceed basically? Can you tell me? Just write out like as we did in earlier questions. Even here, anything can be asked. Like we can ask number of just the F structures on 3. And number of isomorphism classes of F structures on 3. Tell me how can we do that? For example, let's try number of F structures on 3. So we are asking n to be equal to 3. For how many F structures you can construct on 3? Yeah. So for
Three times we have to write this equation. 1 minus x.
Okay. So firstly, what will we do? So for number of F structures, what exactly you will do? Uh, which series you will calculate first? So the type generating one or ordinary one? So again, I forgot the name. Yeah,
Exponential type.
exponential,
Mm.
exactly. Sometimes it is called ordinary also. No, not ordinary, sorry. Yeah, ordinary is without n factorial. So yeah, exponential generating function and generating series, and other is type generating series. So which one you will calculate for to calculate F structures on 3? We just,
Exponential.
yeah, exactly, we will calculate exponential, and you have the cycle, you have cycle index series. So you have everything, so you can always calculate, because when you have the general formula, you can just try to find these two, so you can always calculate. So here what will you do? You'll calculate fx. Fx is your zf, x comma 0 comma 0 up to and so on. Now here what will you get? From the formula you will just put here n greater than or equal to 1 and 1 minus xn. So in the product you will just get what? 1 by 1 minus x, because there is, for the first one you have 1, and from like for the remaining ones you have just 0 0 0 0, right? So is that clear? Is that clear? So 1 by 1 minus x, this will be your exponential generating series.
Okay. N equal to 3, 1 minus x, 3 we don't.
No, don't look at this. You on 3. So firstly you
Okay.
need to see for f structures what you need to calculate. You will first calculate what? You will first calculate the exponential generating series, because you know that in the exponential generating series the coefficients of x raised to power n by n factorial are the count of f structures, right? So
Yes,
you
ma'am.
need to count, you need to find out the number of f structures on n. We are not saying 3 4, it could be anything, like
Okay.
it can be asked anything. Firstly you need to find out the exponential generating series, then only you can do that, because you know that the coefficient will help us to find, to give the value of whatever we need, right? So
Okay,
now,
ma'am.
yeah, so now expand it out. So when you expand, what will you get? 1 plus x square plus x cube. So this is again the same thing. 1 by 1 minus x will be this. Now the coefficients, now coefficients of what? Now here, yeah, so you have this. Now number of f structures, or maybe I'll write directly. You know that the coefficient here, or if you want to write, this is summation x raised to power n. N is greater than or equal to 0. So 1 is there, so greater than or equal to 0. So now the coefficient, so uh, coefficient of, or maybe I'll write x raised to power n will be equal to what? Fn, sorry, this is, so you have Fn, number of f structures, by n factorial into x raised to power n, because you know that you can compare it with Fn by n factorial x raised to power n. So you just compare the coefficient. So 1 is equal to this. So so 1 is equal to cardinality of f structures on n by n factorial. Now you have so here you will get, for all n belongs to n, or better you write n greater than or equal to 1, or maybe that's okay. So this implies what? This implies f4, which you, f3, you need f3, so this will be just 3 factorial, which is 6. Okay, so you can actually calculate for any n. Is that clear?
Yes, ma'am.
Okay. Now now you need to find out number of isomorphism classes of f structures on n. Now when you need to find out isomorphism classes, what will you calculate?
N factorial.
What will you,
It is exponential, exponential,
no, no,
exponential.
not exponential. Now the type will work. So type, this f tilde, the type generating series will give you the count of isomorphism classes of f,
Isomorphic sim classes.
right?
Yes, ma'am.
So now you need to find out the type generating series. So f tilde of x is what? Z f x, x square, x cube, up to and so on. Now this zf x square x cube, now this will give, yeah, this will, here let's see what do we have. We have product 1 by 1 minus xn where n is greater than or equal to 1. So you'll get 1 by 1 minus x, the product is saying, so you have product and n is greater than or equal to 1. And now what you are doing, you're just putting x square, so you can just write x raised to power n. So the formula says this. Now you are putting at the place of xn, you have to put x raised to power n for the type generating series. So you'll get, yeah, 1 minus 1 by x, 1 minus x square, and you go on. Okay, so now let's see what do we need. Now we need to find out, okay, and we can expand it. So 1 by 1 minus x will be 1 plus x square up to and so on. This will be 1 plus x square plus x raised to power 4 plus x raised to power 6. You have to consider the powers. And for the next one, you'll get cubes. So the power of cubes. Okay. Now now you need to find out the coefficient of, so number of number of isomorphism classes of F structures on 3. You need to find out on 3. Okay, so that will be the coefficient of x raised to power n, not x raised to power 3, not by n factorial, right? From the formula you know that there is no n factorial involved. So you got
Yes,
this,
ma'am.
right? So you just need to find out the coefficient of x cube. So let's see what is the coefficient of x cube. This is the product is like for every coefficient, for every power you will get the finite coefficient. This looks like infinite sum, but this is an infinite sum. But for every power you will get the finite value, so you need to find out that. So coefficient of x cube means how will you get. So for the first part, so I'm just trying to calculate the coefficient of x cube. So you have this, I'm just writing it again. One plus x cube plus x raised to power 6 plus up to and so on, and you go on. Okay, 4 and then 8, and this will go on. Now you need to find out the coefficient of x cube. Then so firstly you can just consider x plus x square plus x cube, because whenever you hit x raised to power 4, then x raised to power 4 into something, you cannot get x cube, right? So you just limit it to x cube. Now for the next factor, again you do till x square, because whenever you hit x raised to power 4, you cannot get x cube. Now for the next one, you will just take this one. So I'm just taking the, sorry, not this part, so this part, even cube also, and here this one, here just one. So for the remaining ones, you just take 1 into 1 into 1. Okay, so what you need to do exactly, you need to find out the coefficient of x cube. So you just multiply it and try to find out the coefficient here. So when will you get x cube? So you take 1 here, so start with 1. Okay, fix 1 here. So with 1 you can consider 1 and x. So let's fix 1 here also. So 1 1, and here with 1 you will not get x cube. With x cube you can get it. So 1 into x cube will get from here. The next, so 1 is done. So with 1 you cannot get x cube from any other thing. So when you take x square, then there is no term to take here. Okay, So 1 is done. Now with x, how will you get it? So you can, if you multiply with 1 here and then the next one you have 1 or x cube. So when you multiply with x, you cannot get x cube. So here you need to take x square. So x with x square and here 1. So x into x square into 1. So here you can get, and with x square, when you take x square, if you multiply with 1, you will get 1 x square and here x square. Okay, then x is to power 4. Then x square into 1 or 1 into 1 or x cube. Then you cannot get x cube because there is already x square. So if you want x cube, then you have to multiply with x, which is not here. So you'll not get anything with x square. Now you take x cube. Then you know that you can only consider 1 and 1. So you just take x cube. So you are actually getting 3x cubes. Is that clear? You just need to multiply and just trying to calculate the coefficient of x cube. So you can simply multiply, but you can just directly calculate the coefficient of x cube by looking at the factors. Okay, now the next you need to take 1 into 1 1. So you will get this, you'll get from here only. Is that clear, the coefficient?
Yes, ma'am.
Okay, so very good. So coefficient of x cube is 3. So that is your answer. So this is yeah, this is the number of isomorphism classes of F structures on 3. Actually, I don't know if you know, like this expression, this formula is actually calculates the number of partitions of this is a generating function to for the number of partitions of square bracket n. So like with 3, this is the number of partitions of 3. So you can take 3, 2 plus 1 or 1 plus 1 plus 1. So there are just 3 possibilities. This is the general formula to generating function for partitions of n. Okay. Okay. So I hope this is clear. Can move to the next question. Is that okay? So how to calculate isomorphism classes of F structures, or how to calculate the number of F structures? You can now calculate, right?
Yes, ma'am.
Okay, great. Okay, let's move to the next part. Consider two species of structures S and T, then which of the following is incorrect? Okay, so
Ma'am, one thing
yeah,
about the previous one.
yeah.
So this 3x square coefficient that we calculated, this is the answer. So there was this f3 by Sn, right? That thing. So that thing is 3, right? So that is
F
the okay. So we need 3 means the isomorphism classes in that coefficient was summation fn by Sn
Oh yeah,
x
it's
to the
not by,
power
it's
n.
the number of orbits. So yeah, so exactly what you need to do here. So remove some lines. Yeah. So here,
So this is the
yeah.
okay. So this 3 is the coefficient.
Yeah, 3 is the coefficient because you are getting 3x cube.
X
So you
cube.
need
Okay.
to calculate the coefficient of x raised to power 3 because
So why
yeah.
did we do the previous one at first? Like the fx first we calculated, right?
Yeah,
First
yeah,
we
I did
calculated
that
this.
because I modified the question. So I was saying this is the number of F structures you will get from the,
Yeah. That is true.
yeah,
Yes.
from the exponential part, and for the number of
Yeah.
isomorphism
But
classes.
if the question is only isomorphism class, we can just do the
Yeah,
second part.
yeah, just you can skip to the second part. You can just calculate which we did actually in the second one,
Yeah. In
this
the
one.
second. Yes.
In the
Yes.
second one we just calculated the type generating
Yeah.
series and done.
Yes. Sure. Okay. Thank
Okay,
you.
sure. Okay, let's take this one. So consider two species of structures S and T. So you have two species of structures. Then which of the following is incorrect? So let's see. Now this question is related to isomorphism of isomorphism of species. So when this happens, what happens here? So Sx is equal to Tx, will this imply S is equal to T? So that is the question. So firstly, the question says Sx and Tx. That means we are saying at the level of exponential generating series. So you have exponential generating series. If these are equal, then can you say that these are isomorphism species? That is the question. So can you tell me if this is true or not? This is A part. So you have exponential generating series. So can you guarantee, like, whenever exponential generating series are same, the species will be isomorphic? So let's go to the lectures. So basically there's an example there only, so let's see. So isomorphism of species. So basically, if you can define a bijection from one species to another, then and the diagram commutes. So basically, for all sigma, for all bijection sigma, this diagram commutes. Then this one, this thing, for every sigma this happens. Sigma bijection from, so this is this sigma, then this will be isomorphic. And there are theorems. If f is equal to g, if f and g are isomorphic, then zf is equal to zc. That means the cycle index series will be same. Okay, so yeah, as a corollary, if f is equal to g, if these are isomorphic, then their because you know that if the cycle index series are same, then you just need to put the values as x1, x2, x3, and then you can get the exponential and type generating series. So if the initial one, like if the cycle type index will be same, then these are going to be same. So yeah, that's okay. Now let's see this example. So you take the set function. So e of u. Okay, for this I should change the color. So e of u is equal to u and phi. So if okay. Yeah, where's the function exactly? Here we can see here. So yeah, eu is equal to u. Better to write in a way. Yeah, it's fine. Yeah, so basically eu is equal to u. I think there is one more representation, so I'm looking at it. Yeah, this is your e. Yeah, eu is equal to u, sorry. Yeah, this is enough. Yeah, so here eu is equal to u for all finite set u. Okay, so if you consider this, then you have this example. You have this product I is greater then the cycle cycle index series, you will get it to be this. Okay, and if you take the linear order, so linear order is basically you take x1, x2. So there's an order on the, so you take the permutations and define the order. So then with this linear order, you will get the cycle index series to be this. Then what will happen, as you can see, if I is greater than or equal to 1 minus xi, and here you have just 1 by 1 minus x1. Now you just now when you have to calculate ex, now for ex, what will you do? You will put x1 to be x, x2 to be 0, x3 to be 0, and so on. So here you will just get ex to be 1 by 1 minus x, because others are just 1 by 1 minus 0. So you will just get 1. So ex will be this, and from the second, this zl, you will again put x1 to be x, and there are no terms of x2, x3, x4, so you don't need to do anything. You will just get 1 by 1 minus x when you put x1 to be x and x2, x3 up to and so on to be 0. So these are your exponential generating series. So you can see that these are equal, but the cycle index series are not same. And you know that whenever there is an isomorphism, then cycle index series should be same. So what does this say? You can have exponential generating series to be same, but E is not equal to L. This could happen. So basically this is now again, as you can see, this is the E structures and these are L structures on U. So the count is same. You have the same number of F structures and E structures and L structures on U. But because why are we saying that? Because because exponential generating series are same, right? And exponential generating series is the sum of f structures, count of f structures into x raised to power n by n factorial, right? So that exponential generating series is defined by just number of E structures and L structures. So you can say that these are equal, but E is not equal to L. These are not isomorphic. So this is an example. So yeah. So this is not true. Example from, or I can write z of s. You can just take E because E is for set, and you have z e is not equal to zl, but ex is equal to lx. And this implies these are not equal. That means E cannot be equal to L, because whenever E is isomorphic to L, then their cycle index those should be equal. Okay, cycle index series, right? So is that clear? First part cannot be true, and this is yeah. So this incorrect thing, yeah. Okay, the following is incorrect. So for incorrect thing you are done. Like this is incorrect, but let's see the other parts also. Yeah, okay, it's fine. So zs is equal to zt. Now it is given that cycle index series are same. Then will that imply that cycle generating series are same? Is that okay? B part. B part. Okay, so for B part, okay. So basically you know that zs is equal to zt. Now what you will do for to calculate the uh, cycle generating series, you need to put x1 to be x, x2 to be x square, x3 to be x cube. Okay.
Yes, ma'am.
Yeah, yes. Okay, so you just put it when you know that the initial function is same, then these has to be same. So this is correct. What about the third part? S is equal to T implies this. This is exactly the theorem. If S is isomorphic to T, then this has to be the same. And similarly, this is okay, because whenever S is isomorphic to T, then Sx is equal to Tx, because the cycle index series are same. So this exponential series has to be the same, right? So all these are
Yes, ma'am.
okay, but the first part is not. Okay, great. Let's move to the next question. Does there exist any species of structures with fx is equal to 1 plus x square by 2, x plus x raised to power 4 by 7, zf x1 x2 up to and so on is equal to 1 plus log 1 minus x cube? Okay, sorry, I'm just reading it. So let's consider the first part. Okay. Just give me a minute. I'll be back in a minute.
Intima.
Yeah, I'll share again. Yeah. So, what do we have? Does there exist any species of structures with fx is equal to this? Let's see. So, you have, yeah. So, what do you need to see? Like, can there exist any species of a structure with maybe the exponential generating series, maybe type generating series, or maybe cycle index series? So, uh, can we have with these values or not? That is the question. So, let's start with first one. So you have fx to be equal to 1 plus x square by 2 plus x raised to power 4 by 7 plus up to and so on. So what do you think? Like what should we check? Here we have exponential generating series. So what can we see here? What should we try? Okay, with exponential generating function, what is the information we have as we have seen earlier?
Summation of Fn into x power n by n factorial.
Yeah, exactly.
Fn
Yes, we have this information with as
exponential
f.
to
Yeah, with
f of x.
uh, yeah, f of x is equal to this. So we have this information with us.
Yes,
Now,
ma'am.
what do you think? How should we see that there is some existence of any species of structures with this exponential generating series? What should we look at?
So coefficient of x to the power 4 is 1 by 7
Yeah.
equal to if you f 4 by n factor 4 factorial is equal to 1 by 7. If you do that, then I think we can see that this cannot be possible
Yeah.
because it has to be integer. This f mod of f and f4, I mean.
Exactly. Very good. Yeah, exactly. So, yes. So, what is the problem? Because here you know that this thing should be an integer or maybe a positive number. Okay, it should be greater than or equal to 0. It's an integer. Okay, so fn is something which cannot be rational. So here if you see x, you have x raised to power 4 by 7, that should be equal to f4 that should be equal to this. Now if you compare it, you will get f4 by 4 factorial. Now what will you get? 4 factorial by 7 f4, and this is exactly, you can see that there is this, you cannot write it as an integer because 7 will not cancel from the numerator. So this does not belong to z, or maybe this is not an integer, so this cannot be possible, right? So this is not possible, so this cannot be a exponential generating series for a question. Is that okay? So this is not possible.
Yes, ma'am.
Okay, great. Okay, let's see the second one. So second says ZF x1 x2 up to and so on 1 plus log 1 minus x3. Okay, now you have given the full function, the full cycle index series. Now how should we check or how should we try? Can you tell me?
Again, do the expansion on the right hand side of the logarithm function, and
Okay.
then on the left hand side it's this fn by sn x to the power n thing. So
This is
the
cycle.
other,
1 second. This is cycle index series. So you have
okay,
nothing in no information with cycle index series. You have just the main formula which says like you have fixed points. You have to consider the stabilizer of Fn with respect to F sigma if I'm not wrong. So this is something which you need to calculate. With cycle index thing you have that one big thing, the main formula. So if you are going to compare, you have to compare with that formula. So that is something like F n F sigma. Yeah. So these are the stabilizer, and there is some cycle type formula, cycle type thing. One two. This is like that something. So some coefficient in this form, or maybe I guess n factorial. Yeah, it's there. Yeah. So yeah, how shall we try there? So you have cycle index series here. So yeah, we can expand it, but you have to compare with this thing.
so
Yeah.
the one definitely comes from the identity, which is like x1 to the power 0, x2 to the power 0. I mean, not 0. Identity permutation means like
No,
that
identity
thing.
permutation will be like, acha, you are saying if you take, no, actually x raised to power uh, sigma 1 will be like all n. Like you are saying the identity, then identity means as we have done in
Ma'am, here
exponential
we
thing.
find number of permutation,
Yeah, number of
cardinality of
permutations. Yeah. Yeah, you can try to
fn
find.
powers f of sigma.
Yeah, it's not power, it's the stabilizer, yeah, which fixed by
Ah,
F sigma.
stability.
So all those S belongs to Fn,
Hmm.
which are fixed by F sigma.
Fn. Ah.
Yeah, so that is this count. So what you can do, you have cycle index series. So from that you can always get all the other series, right? Because this is very complicated, this stabilizer thing. And so for comparing, you should have something which is very strong or something. But you can go to that if the other things will not work. Certainly you can go to the cycle index and compare it, and you can try to find if that exists or not. But you can also try. So what I'm saying, you have this much information, cycle index, so you can definitely try to find exponential index series and the third one, so cycle index series, sorry, not index, generating series. And this is cycle generating series. Okay, so here let's see what is happening. So here you have, so exponential generating series will be what? You will put x 0 0,
0, 0, 0.
right? That is your fx. What will it be? Just put it here and you can get the value. What it will be?
X.
X. You have to put x1 to be x, x2 to be 0, x3 to be 0, and everything else to be 0. Everything will be 0.
One,
Just
one,
one.
one.
Yeah, exactly. So you have
Mm.
log 1 minus 0. So you'll get 1 plus log 1 is 0. So you get 1. Okay. So you have 1. Now, now let's calculate the cycle generating series. So you will get ZF x x square x cube raised to power 4 up to and so on. So that is your f tilde x. So now you have to put, you have this log 1 minus x4, sorry x3. So what will you get? 1 plus log, so x3 is your x cube, right? So this is your x1, x2, this is x3, right? So now
Mm.
let's expand it out. What do we have? What is log 1 minus x cube? Again the same formula which we used earlier, I guess. So this is log 1 plus x is equal to
X.
yeah, x
X
minus x.
minus x square by 2 plus x
Yeah,
3 by 3 minus
exactly.
x 4 by 4.
Yeah, so from this you will get 1 minus x to be, you will just put at the place of x
X
just minus.
minus minus.
Everything minus, right? Because this will
Yes,
be
ma'am.
square. Yeah. Okay. So here you will get 1, sorry, not 1. You will get x minus x square by 2 minus x cube by no, not this. Now you have x cube, right? So you will at the place of x you have to put you
Cube.
have cube. So you will get cube here, and the next term will be 6,
6.
and 2 will be there. So here you will get 3 into 3 9. Yeah, like this. I'll again erase this. Okay. So here you will get 1 minus x cube minus x is to the power 6 by 2 minus x is to the power 9 by 3 minus up to and so on. So what can you see here? Now you have two information, as I said, fx to be equal to 1 and f tilde x to be equal to 1 minus x cube minus x raised to the power 6 by 2 minus x raised to the power 9 by 3. Yeah. So what do you think? What do we have? Like from this much information, uh, what can you get? Can think of something? I'll again say compare with the original, compare with the main thing. So which we started with. So you know that fx is your,
So fx,
yeah.
can we say something about the coefficients? Like, uh, so total coefficient f2 for no, what is it said? Mm,
This fn, you mean?
yeah, fn
Yeah.
f2, yes. Say for example, from fx that will be 0.
Hmm.
But no, not f2, but say f3.
Yeah.
From fx, this f2 will be coefficient 0, right?
Yeah.
And like so total number of combinatorial classes,
Yeah.
and but this total number of isomorphic classes, that
Mm-hmm.
is minus one. No,
Oh.
how do we interpret from f the
Yeah, yeah,
f
yeah. I
part
got it.
this thing?
Yeah, there should not be a minus, I think. Hmm. Yeah, that is exactly the reason. But how should we interpret about minus? I think we can modify the question because I just made it. So even though if I keep plus, that will be still, but we can get negative, right? 1 second.
Okay, so there was a modulus, right? So this
No,
is
no, no.
minus, but
There's no
uh,
modulus. That is cardinality.
okay.
Yeah, that is not modulus. Let us see. We should not get actually negative, I think. Uh, that is some made up question, so we can always discard from that value also. But just to be sure, yeah, these are as you can see, this is a count, and this is a count, and this is some product, so you cannot get negative, right? So as you can see, okay, I am looking at the theorem, but yeah, maybe at this place. So is the exact formula. Yeah, cycle index series is this. Yeah, here you can see this is some count, and these are x1 raised to power sigma 1, and so this cannot be negative. There is no possibility of negative here, so that is also one thing which discards that. But yeah, so that's some made up question, so we can always, yeah, for example, if we have positive, so to make it positive we can actually do this. We can just put minus outside, right? Even with negative sign, you can say that this is not possible. Okay, so here, yeah, but better to modify with this because, yeah, so you'll get negative, 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 and you will get negative outside, and this is this. So here 1 plus x cube plus x raised to power 6 by 2 plus x raised to power 9 by 3. Yeah, so you have plus here everywhere. Yeah, and exactly as you said, very good. So this is something which you can say, because fx is what? Fx is the summation n greater than or equal to 0 with with fn, the cardinality, into x raised to power n by n factorial, and on the other hand you have f tilde x to be the orbits x raised to power n, and this value is itself says this is the number of f structures on n, and this value says number of combinatorial classes, sorry, not combinatorial, this is
Isomorphism.
yeah, these are two different terms, right?
Isomorphic structure.
Yeah, isomorphism classes of f structures on n. Of n. So this certainly says that this count should be bigger. Number of f structures, this count on n or of n, on n, that is better. This, because this is the isomorphism classes, so you are just so isomorphism, two classes will be fu, will be same as like sigma belongs to fu, and sigma and for example tau belongs to fu. These will be same if you can get isomorphism, which if you can get Sn, like any element of Sn such that psi of sigma is equal to tau. If you can get that, or maybe SNT, that was the example. that has been used. So number of isomorphism classes of F structure on it. Right. So because of this, you can see that now you know that F tilde x is given to be 1 plus x cube plus x raised to power 6 by 2 up to and so on. Now x raised to power cube. So coefficient of x cube is 1. So number of isomorphism classes of F structures on 3. Now we are in 3. So with 3 you know that there is 1. But as you can see, Fx is given to be just 1, that is just 1. So you have number of F structures on 3 is equal to 0 because there is no term of x cube. So even n factorial will come. So whatever, you have 0 number of F structures on 3. So that means, and you can see that isomorphism classes are bigger than this, so that cannot be a possibility. So this is not possible, and you are done. Okay, is that clear?
Yeah.
Okay, let's move to the next part. Yeah, F tilde x is equal to 1 by 1 minus x. So third says F tilde x is equal to 1 by 1 minus x. So what do you think?
Correct.
Yeah, and how?
It's exponential.
Yeah, so exponential what? Yeah, this is like
This expansion is summation of x power n.
So you need to come up.
Expansion.
Yeah, so you need to come up with an example of F structures, F structure on F structure, species of structure, such that F tilde x will be equal to 1 by 1 minus x. Do you have any example? Because that will guarantee only, right?
Yes.
Existence means there is some example. There is some.
So f of n equal to n factorial.
F of x.
Sorry.
F
No,
of
instead
n.
of x. If we using exponential generating series, z f of x comma 0 means we get 1.
No. One more thing. You cannot go from this to fx. Never. Because where will you put it? Because x1 has been in this f tilde
Cyclic.
x.
Okay.
Yeah.
The expansion. Yes, ma'am.
Yeah. So this
F
is
of
x.
x is equal to, that expansion is 1 plus x
One
square.
plus x cube, etc., etc. So
Yeah. So you
I
you
have
can. Yeah.
number of isomorphic classes fn.
Yeah.
That is equal to
Yes, ma'am.
n. That is equal to 1. Fn equal to 1 for all n.
Yeah. So you have not fn, the orbits. So
Yeah.
so the orbits basically fn
By Sn.
Equal to n.
yeah, orbit.
How I don't know how to
Sorry.
pronounce
F
that.
sigma.
Yeah, Sn.
F sigma.
Yeah, Sn orbit by Fn.
F
So basically
Fn.
orbits of Fn with I think Sn. Okay, how shall I say? Basically, this is something, all those Sn into sigma S, where S belongs to Fn. If I'm not wrong, this has been said that Sn, the set of Sn where with orbits as Fn, something like that maybe. Anyway, like you can check that. So yeah, these are the orbits. Now yeah, this much information you have, and this cardinality says this is equal to 1. Okay, so yeah, this is something there. But you can also try the examples you have already. Is there any species of structure which has this uh, what is this f tilde? So basically this is cycle
Ma'am,
generating.
ma'am, orbit means image. That cycle means where it goes to. Domain and codomain we have just image, and fixed means we take one image and we get one unique image. And the stabilizer means what we get if we find image one, the image should be in codomain one only.
uh yeah, so basically what is
And
happening if,
how
yeah, so
uh,
you
here
mean,
orbit is
okay, so this is okay, so orbits are basically, this is coming from group action. So you have this, uh, this goes like that. So you
mm,
define a for example sigma into s comma s is equal to, let's say, sigma s. So you are considering, so you consider Sn into s and do this. I can show you if you want. So has used here. Where is it exactly? Yeah, this is here, and yeah, the formula. Yeah, these are the fixed points, and then you want to write it as like this. Then the, okay, meaning. Okay, if you want to exactly see the main thing, you can see that in, yeah, cycle index polynomial. Sorry, is, I guess, counting, yeah, orbit counting theorem. So yeah, this is this, if you want to see. U belongs to u, and you just take it. And yeah, so GU is basically u. So if G is this G sigma, then you just consider all the uh, with all
generated.
G, you just consider that this is called as orbit cycle of sigma to which you belong. So yeah, it's like that. And when you ask for the stabilizer, so stabilizer is like okay, here there's new notation, this orbit counting theorem, this even we are using as Burnside lemma. So this is exactly, you take GEU, and then U sigma is like which fixes the elements of U which are fixed by sigma. Then yeah,
So,
so yeah, these are the, you can go through this orbit counting theorem and the earlier one to just familiar with the notations. Okay, anyway, so we have this now. Okay, as I was saying, it's very hard to definitely figure out if this is exactly uh, uh, like there exists a f structure which a species of a structure with f tilde x to be this. So why I am saying that, so we can always think of the standard examples. So if you go through the examples, and we have discussed as a counter example to previous question, earlier question also. So what I'm saying, you consider this f zf. So you consider the linear order species. Then you know that this is equal to x1 x2, this is equal to 1 by 1 minus x1, right? This is from the linear order. And yeah, that I can again refer it to. I'm just keeping the notes because that's easy to always refer. So yeah, for L, Yeah, species of linear order. Yeah, so you take a species of linear order, then you know that ZL will come out to be 1 by 1 minus x1, right? Now, you know that if you consider that, then z tilde, sorry, not z tilde, that is f tilde, or maybe zl x square x cube, this will be equal to 1 minus 1 by x1 is x. So you have this. So there exists a f series, species of structures, f species of a structure, such that f tilde x is equal to 1 by 1 minus x. So it's very hard to check definitely if you have if you can find out something or not, because you have to go through the process and you have to figure out the coefficients, and then you try to build like go back to find out what exactly you can have this species to be. So it's hard, but I just kept this example because this is something we know, that linear order, so you can do that. But yeah, it is definitely hard to figure out if there exists, like if there does not exist, you can get the idea from this part, if this helps. Otherwise, next level could be hard. Is that okay? Just consider the species of linear order. Is that okay?
Yes, ma'am.
Okay. Yeah, this was the last question from my tutorial. You may ask other questions if you have.
That automorphism, number of automorphism we have now, ma'am.
Yeah. So
We find the degrees.
okay. Yeah, exactly. So do you want me to discuss those questions which were in the last time, like in the
Automorphism.
So how
Second
to
question.
find? Yeah.
Number of order of
Yeah. So
automorphism.
I can actually discuss those two questions, two or three, whichever are there. Just give me a minute. Mm-hmm.
మన చికెన్ సాఫర్.
So that was week 5, right?
So there is a star graph.
Yeah.
And what is the order of the automorphism group of the following graph?
Okay. Yeah. So star is
First, we
right.
have to find the degrees.
Yeah. So okay.
And
Discuss
1
it.
degree we have 6, and all others degree we have 1. So
Yes.
sigma of V1 equal to identity, and V2 means we can give 6 possibilities, and V3 means 5 possibility,
Yeah.
V4 means 4 possibility, V5 means 3 possibility, V6 means 2 possibility, and V7 means 1 possibility. So multiplications 6 into 5 into 4 into 3 into 1 equal to 720.
Yeah.
Yeah,
Exactly.
okay, but can you explain a little bit more?
Yeah. I'm doing that. Okay. 1 second. Yeah. So I'm doing that. Okay, so what she said, because I explained, we discussed that in the week 5 session, so that morning session. So yeah, that the question was, you have this I guess a star, so there are 7, right? So you should
Yes,
have,
ma'am.
okay, I don't know where exactly it lies, but yeah, I'll just try 7. So 1 6 I should have. Okay, okay, I definitely made more. So okay, let's do 6 1 2 3, right? So for example, you have this, was that the question?
One more.
Order of
7.
One more.
order of automorphism.
Yes.
One more. So is it 7?
So
So there are 8.
No.
Then
7. Sorry.
yeah, so
Remove
the
that.
yeah, so you
Now
have
it's correct
V1,
now.
V2, V3, V4, V5, V6, and V7.
6.
Okay, you
Yeah.
have this. Now you need to calculate the yeah. So now you need to calculate the how many automorphisms you can have of this graph.
Order of automorphism group.
Yeah, you can say that number of automorphisms, or you can say same as order of automorphism group, the cardinality of automorphism group.
Yes, ma'am.
Okay, of this graph. Right, so let's see how can we do that. So what do you have now? You calculate the degrees. Okay, degrees, as I explained earlier, so I can explain again. So automorphism, firstly, what does automorphism mean? Automorphism mean,
Isomorphism from that set to itself.
yeah, and what does that mean? So automorphism sigma of any graph v comma e. So v is the set of vertices, e is the set of edges. So
Mm.
this sigma will be what? Firstly, it will be a bijection of any graph v. So there will be a bijection from vertices to vertices. First thing, so this is a bijection.
Yeah.
Second thing, sigma. So if there is like v1 to vi, for example, yeah, if there is like vi and vj, you consider two vertices, and if there is any edge between them, then there must be a edge between vi and vj, sigma of vi and sigma of vj.
Yeah.
Okay, that is the definition. Right, now,
Okay, so you
yeah.
are saying that sigma of v1
Hmm.
can go to 6 places
Yeah,
because
exactly.
the degree of v1 is 6.
Yeah, you know the
So
degree what.
sigma of
Hmm.
v1 can go to 6 places. Sigma
Hmm.
of v2 can go to
No, no, no.
5.
One second, one second. V1 can go to where?
V1, I mean sigma of v1.
Hmm.
So there are like 6 options for that.
For with the first
I mean,
part.
it can be V2, or I mean sigma of V1 can be V2 or V3 or V4 or V5 or V6 or V7.
Actually, not. If you are talking about the automorphism, for the first part, it's okay. You need to define a bijection. You can just permute the 1, 2, 3, 4, 5, 6, 7. Okay, but for the second part, you are saying that there should be a edge between vi and sigma vi and sigma vj whenever there is an edge between vi and vj. So let me define one more thing here. So here, now let's come to what is the degree of any vertex v. So degree of any vertex v means,
Degree, I know. Degree means that number of adjacent elements. So
yeah, or
basically,
maybe number
V1's
of
degree is
edges
6.
coming, yeah.
Number of neighbors,
Yeah,
basically.
exactly. Number of neighbors, number of edges coming out of it. You can from v, or whatever you can say. Exactly. So
Yeah.
you have, so sigma of v1 is 6, sigma of v2 is v2 is 1. There is just one.
One.
Okay.
Yeah, so what I am not understanding is why the degree is the this sigma of V1. Why is the degree is sigma of V1? Why is degree of V1 is equal to sigma of V1?
Oh, sorry, not sigma. Yeah, sorry. This is degree. Yeah, that was. Yeah, these are degrees.
Okay.
Yeah,
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 yeah.
yeah. I'm just
Okay, now
writing the
makes.
degrees right now.
Yeah, that makes sense.
Yeah,
Okay.
so V5, degree of V6, degree of V7. Okay, so these are all one. Okay, now let's come to the main thing. Now one more thing we can say when we have introduced degree. If there is an automorphism, if sigma is a automorphism, then for all v belongs to v, degree of v should be equal to degree of sigma of v. So what I'm saying, if you define automorphism,
Yes.
then degree of v has to be equal to degree of sigma v. Why are we saying that? Because this second condition will make sure that, because if there is a neighbor, so you have v1 now, or maybe like vi. Now there is vi is connected to number of degrees, like so the degree count. So there are these many. For example, you have 4 edges, right? Now when you move it to sigma of vi, it should also have 4 edges, because you know that whenever there is, we are not saying with what, but at least the number of edges should be same. Because with vi I am saying there are 4 edges has to go, like, yeah. So we are saying there are 4 edges. So to whatever we don't know, okay, let's say the degree of vi is 4. That means it should have 4 edges. That means there exists 4 vj's such that there is an edge. So vi is connected to some vj1, then connected to vj2, connected to some vj3, connected to some vj4. There are 4 elements to which it is linked. There is an edge between them. So there are 4. Now when we are saying this is happening, vi is connected to 4 the different elements, then sigma of vi has to connect to some 4 elements, right? Because sigma is a bijection, so those has to be distinct. So sigma of vi should have 4 degree, right? Is that clear?
Yes.
So whenever there is an automorphism, then sigma of vi and sigma of sigma of v and v has to have the same degree. So that means degree of v1. So degree of v1 is 6, and there is no other element with 6 degree. That means v1 has to map to v1. So firstly we have this identity one. Okay, so identity is always there. So let sigma is a bijection.
Okay, I understand completely now. So
Okay.
V1 has to map to V1.
Yeah.
V2 can map to 1, 2, 3, 4, 5, 6
Actually
choices.
6. Yeah.
And V3 can go to the remaining 5 choices, etc. etc.
Yeah,
Okay,
exactly.
okay.
So 6
So,
factorial.
okay. Now I understand how to do this kind of problem. Okay.
And one more thing, there is one catch here. So here there is no issue, because these are symmetric in the sense
Yes,
that,
yes.
yeah, these are symmetric means there is v2 and you can map v2 to v3, or because it is connected to v1 only. So we know that there is one connection we need, v to v1. So if v2 will map to v4, then v4 and v1 will again have the same there will be an edge, one edge. So that is okay. So for example, if we consider this example, week 5 live session, yeah. So this one, for example, which we discussed last time, yeah, this one. So if you have this kind of image, so because degree is one option, but this is not enough. You have to check the other thing also. Oh, sorry, I did copy. Yeah. So this is this. Yeah. So let's see here what is happening. Again you will check the degrees. So degree of v1 is 2, degree of v2 is 3, degree of v3 is 3, degree of v4 is 2, degree of v5 is 4. So now you can say that v5 will map to v5 for sure. Okay. So there is firstly identity automorphism, that is always there, so let's discard that one automorphism we have. Let's count the other ones. So v5 will map to v5, that has to be there, because with 4 degree we have one option only, so v5 will map to v5. Now let's see the other ones. So v1, now v1 and v4 can map to each other because the degrees are same, and v2 and v3 can map to each other, right? So what options we could have, either v1 will map to v1 itself and v2 will map to v3. So one identity one is always there, so let's discard that, and let's say sigma is not equal to identity in this condition. So v5 is mapping to v5. Let's say v1 is again mapping to v2, sorry, v1. So whenever v1 is mapping to v1, then v4 has to map to v4, because there is one option, v4 or v1 can switch only. And if we are saying v1 is mapping to v1, so v4 has to map to v4. Now what can happen with v2? v2 either map to v2, then it will become the identity one, because v2 will map to v2, then v3 has to map to v3. So let's say v2 is mapping to v2, okay, sorry, v3. We are going beyond identity. So v2 is mapping to v3, then v3 has to map to v2, right? There is this one possibility. The other possibility could be v5 is mapping to v5, or yeah, okay, I'm just writing the possibilities first. Now what can happen, v1 is mapping to v4 and v4 is mapping to v1, these are switching, and the others are remaining as identity. There is this one option, and now next option is v5 is mapping to v5, v1 is mapping to v4. Now both of them will switch. Okay, is there any other possibility other than identity? So identity is there. Now these three could be a possibility with the degree argument. Is that okay?
Yes. There are 4 options.
Yeah, now there is a problem. Now let's see what could now we have to authenticate that these are the possibilities for sure. Okay, let's see the first one. Now first one, what is happening, v5 is mapping to v5. Now v1 is mapping to v1 and v4 is mapping to v4. Now let's take let's think of v1 and v2. So we know that there is an edge between v1 and v2. So the v1 and v2 has an edge, right? Now from the automorphism thing, sigma of v1 has to map to sigma of, like sigma of v1 and sigma of v2 should have an edge, right? v1 and v2.
Yes,
So
between them.
yeah, so now what is sigma of v1 in this case? Sigma of v1 is v1 and sigma of v2 is v3. Is there any edge between v1 and v3? There is no, right? Because there is no connection between these two. So I'm saying, so degree is not enough. So this condition, this cannot be a possibility. So you have to next level check, like are the ages okay or not? Like we can discard some options by using degree argument. Now we have to maintain those two conditions also, like we have to verify whether those two conditions are true or not. So first condition is bijection, that is okay, but now the age argument. So for example, this is wrong. Now what about the other one? v2 is mapping to v2 and v1 is mapping to v4. Again take v1 and v2. So v1 and v2 has an edge. Now v2 is mapping to v4 and v1 is mapping to v2 and v4. These two should have an edge, right? So is that the condition? v1 v2 and v4. Is there any edge? No, right? So this is again cannot be a possibility.
Okay.
So we are left with this one, and that is true. We can check that. Let's check that. v1 and so again v1 and v2 has an edge. So v3 and v4 should have. So v1 and v2 has an edge. So v3 and v4 will have. That is okay. So what is happening? Both are switching. So both are switching. So both are going to the other side. So so that will maintain the thing. So again, you can check with the other thing. So you have V2 and V3 as an edge. V2 and V3. So other side also V2 and V3. So we just need to check other thing. So for example, V4 and V2. So V4, those are not connected. So V1 and V3 should not be connected. That is okay. So you can check all the possibilities. So degree argument
Is
is
it
not.
necessary to maintain the same neighborhood? I mean, why necessary that V2 and V4? I mean, why is that because V2 and V4 don't have an edge in the original graph, so in the other one it cannot have.
Yeah, because
In
that is the condition, right? So what we started. So what is the definition says? Definition says these two conditions should hold. Definition says there should be a bijection, and whenever there is an edge, there should be the edge between the images. That is the requirement. Yeah, we are not putting something extra. These are the conditions which need to be verified. So the main thing
Sure,
is,
okay.
so what I want to say, there's an edge between vi and vj. This implies if and only if there is sigma vi and sigma of vj has an edge.
Yes, I did not consider the
Yeah.
fact that if there is not an edge between Vi and Vj, then there is not an edge between sigma Vi and sigma Vj.
Yeah, that is also true. And even the other thing, like, because v1 and v2 has an edge, so their images should have it. So for the first two condition we are not getting an edge, right? So v1 and v2 are
Uh,
having it, then v1 is mapping to v1 and v2 is mapping to v3. Then v1 and v3 are not having an edge, so that is a problem. So whenever there is an edge between them, there should be an edge between the other, in
yeah.
between the images. So the main thing is, this implies that degree of vi should be equal to degree of sigma vi, but not the other way around. So these are true for all I and j, and similarly this should be for all I. So I'm saying this implies that degree should be equal, but these are not all. Like this is not the full condition. Like you have to check the edges argument, edges. Uh, like there is an edge or not. So you have to check the main condition also. So degree is not enough. So other side you cannot guarantee, like if degrees are equal then there will be an edge. You cannot say that. So yeah. Are there any other question related to this? There were, I guess, 3 or 4 questions in the assignment. So I tried to cover that in the last week. So I discussed these two.
Question number 14.
Okay, so can you tell me what is the question?
Let tau
Hmm. Let tau.
denote the cycle graph with 6 node. Let G equal to automorphism of tau 6. What is the number of G equivalence classes of colorings of the vertices of tau 6? Okay, so I'll
Oh,
read it slowly. Tau 6 is the cycle graph with
yeah,
6
yeah.
nodes.
Okay, with 6 nodes. No? Okay.
Then
Mm.
G equal to automorphism of tau 6.
G is the automorphism of tau 6.
Then what is the number of
Cycle index.
Yes.
G equivalence classes of colorings of the vertices of tau 6 with
Yeah.
2 white, 2 black, 2 green vertices.
Okay. Right. Yeah, that was the question Mahalakshmi you were asking right last time, right?
Colors. How many colors? 2 beats, 3 beats.
Yeah, related to D6, I guess. That was the question?
That is cycle index is different from rotation and the
Yeah.
dihedral reflection formula. Now, madam asking coloring nodes. We
Okay.
have coefficient. After we
Okay.
finding that, we find a coefficient.
Yeah,
Two
yeah.
beats,
So,
three color.
I got it. Yeah, you are asking for the Polya enumeration, I think. Yeah, this type of question. Find the number of 4 2 necklaces with 2 beads of one color and 2 beads of other color.
Yes, ma'am.
Yeah, this is kind of the same question that I discussed as a sample question last time. So yeah, that was the thing. So what you need to do, you need to firstly take G. So there are 6 nodes, so you can consider the automorphisms of those 6 nodes. So what the question begins with? Can you tell me the first
G,
line?
uh,
Mm-hmm.
yeah, so
Share your
G is the
screen if
auto.
it possible means.
Sorry.
Madam,
Yeah.
another madam.
Yeah. Yeah. Yeah.
Her name's
Uh,
share your question
Shantini. Yeah.
if you are using.
Yeah, the first line, I guess,
I,
I'm asking
you
because
want me to share the question? I mean, share the screen.
uh,
Yes. You
yeah, you
share,
can
ma'am.
do
You will
that. Yeah,
be
that will be
enough.
great. Yeah, I'll stop share. Mm, yes, yeah, you can do that.
Ma'am,
Uh,
Yes,
okay.
you're able to share. I guess there will be no host file.
Well,
Yeah, yeah,
let
sure,
me
sure. Take your time.
first.
I got 100.
Sorry.
Tag one
I
into
got 100 last assignment.
home screenshot.
Uh, yeah. Okay. Yeah. That was I was asking. A cycle graph is given. That means there is a cycle. So you need to consider 1 to 6, and then you need to consider uh, all the 6 nodes. So what I was saying, yeah, I'll take a screenshot of this and then maybe, yeah. Okay. Yeah. Now you can. Now I'll
Stop
try to.
sharing.
Yeah. You can stop share. Thank you. Yeah. Yeah. So what we need to do, so you have something like the question says, so there's a, yeah, so automorphism of tau 6 is a cycle graph. So cycle graph, why I was asking cycle graph, because we need to consider G to be a subset of S6, but what exactly is that, it depends on what is given. So you have a cycle graph. That means 1 2 3 4 4 5 6. That means you G is actually generated by 1 2 3 4 5 6, the cycle 1 2 3 4 5 6. So you consider that and you take all the, so you will get 6 elements. So you'll get 1 2 3 4 5 6, and you will get 1 2. So in the square thing, it will map to 1, will map to 3, 3 will map to 5. This is a way to do that, so I'm doing that. 4 6 get, so this is sigma, let's say this is sigma, then this is sigma square. Sigma cube will map the third element, so you'll get 1 will map to 4, 4 will map to 1, so this will be this, 2 will map to 5, 3 will map to 6. This is sigma cube. Sigma raised to power 4, you map to the fourth element, so 1 will map to 5, 5 will map to fourth element, so this will be 3. Yeah, and 3 will map to 1, so this will close, so 2, and then you'll get 6 and you'll get 4. Okay, this will be sigma q, sigma raised to power 4, and then you will get sigma raised to power 5, that will be the inverse, so you can just write 1 6 5 4 3 2. Yeah, and if I'm not wrong, yeah, so basically you can just invert it, so that will be just 1 6 5. Yeah, I was writing right. 1 6 5 4 3 2. So these are the ways to just write it down. So that is the inverse, and you will get the identity later. So you got these 6 elements. Okay, Now you need to find out using Polya's enumeration. So what does that say? So yeah, that is some formula. So you need to consider all the p. So I can go to that formula. Yeah, you need to find out this summation. Okay, 1 by mod g summation sigma belongs to g, p mu sigma is the cycle type, x1 x2. So you need to expand it. So these are the symmetric polynomials corresponding to x1 x2. So these has the exact values which is coming from the notes itself. I'm not doing something extra. So this is like, okay, so firstly whatever has been asked you need to I'll write first that and then I'll explain. So you will do 1 by mod g summation. Here you will get I forgot again, sigma belongs to g, p sigma, yeah, mu of sigma. So
Mu sigma
yeah, exactly. Now how many
x
yeah, you will,
x6.
yeah, how many exercise you will take, that will tell you the question. So question says yeah, the question says how many colors you have, k. It will go up to k, and k are the number of colors you have. So the colors you have, uh, classes of curlings of the vertices of gamma 6 with 2 white, 2 black and 2 green vertices. So 2 white, 2 white, 2 black and 2 green. Okay, you have this. So you have to choose 3 colors. There are 3 colors which are involved in the case. So you need to calculate this value. So mod g is yeah, 6, and then summation is over sigma. So there are 6 elements. You need to expand it over all the elements. So firstly let me write tau here to not confuse it with that sigma which we have said, that this sigma I'm seeing this to be sigma. So you take p sigma of mu of sigma. So mu of sigma is what? Okay, I'll write it first. Okay, so that you'll understand this. So there is 1 by 6 outside. So p mu of sigma square x1 x2 x3 plus p mu of sigma cube. We'll do it for all of these. Mu of sigma raised to power 4 x1 x2 x3 mu sigma 5. We need to calculate all these. We need to actually find the coefficient of, okay, I'll tell you one second. This is identity, mu sigma raised to power 6, identity with 6 elements, of 6 elements. Okay, so 2 white, 2 black and 2 green. So what we need, we will expand it, we will get whatever we have. We need to find the coefficient of, in this polynomial, coefficient of x1 square, x2 square and x3 square. We need to find all the possibilities, like all the coefficient of x1 square, x2 square and x3 square. What does this say? This is first color will come twice, like for 2 beats. For the second color will be repeated twice, and the third color will be repeated twice. So this explains that the powers is because x1 x2 x3 are representing the colors, different colors. So this will give the, so the coefficient of this will give you the answer. So let's calculate it. So what is this? This is the symmetric. So this is from the formula itself. So mu of sigma is what? Let's write the, what is the cycle type. Sigma is 1 2 3 4 5 6. So the cycle length is 6. So this is just 6. 0 we will not write. Now again p mu sigma square. Sigma square has the cycles 3 cycles, right? So you will get 3 comma 3. So I'm just writing the cycle type. Now with mu sigma cube has 3 cycles of 2 length. So 2 comma 2 comma 2. Sigma 4 has 3 cycles of two cycles of 3 length 3 comma 3. and again mu 5 is of cycle length 6, and you have identities. So you have 1 comma 1 comma 1 comma 1 comma 1. You have one length, 6 cycles of length 1. Okay, so this is this. Now what you can do, you can just you can remove this, because 6 is coming twice, so I'll write 2 here just to simplify, and again I can remove this and I can write this. So you have exactly this much value. Now you need to calculate this. And what exactly is this formula? This formula says 1 by 6 2. This says you take the powers. You take the powers of this length. So that is the formula to expand. Plus 2. This says x1 cube plus you write it. You write as these are symmetric polynomials into there are 3 cycles, like you will expand it for each coordinate of this cycle type for. So you'll get x1 cube. So again you will write it, so I'll write it as square because there are 3. Okay, if you need I can show you the formula also. Here is it exactly in the notes. So this for this 2 there are 3, so it will be repeated thrice in multiplication. So I can write q, and then x1 plus x2 plus x3. Now you take, there are 6 of these, so you'll write it in the multiplication, so you'll get this. Now you need to find out the coefficient of x1 square, x2 square and x3 square. Let's see where exactly it is coming. So 1 by 6 is there. Now let's see from the first term, will you get squares? No, you cannot get it because okay, this cross is not, because you cannot get x1 square from here, so this addition is of no value. Now let's see from the second part. So this second one is square of x1 cube, x2 cube. These again you cannot get it because already these are in cube powers, so you will not get from here. Now let's see this part. This one will definitely have something because there are squares involved. So if you want to write, you can actually write it 3 times because that will be a requirement. Now let's see how many these x1 square, x2 square, x3 square you will get. So from here you multiply with this and multiply with this. So from this you will get 1. Now you multiply with this and this, with again same thing. Okay, so there are 2. Okay, from x1 square you will get 2 again. If I miss something, let me know.
Ma'am, this is okay. I can do this calculation.
Okay, so
one thing, can you once tell me what will be, say, this is not from this particular question, but just example. What will be p of, for example, say 3, 2, 1 of x1, x2, x3?
3, 2, 1
of x1, x2, x3.
Yeah. So basically what you need to do, the formula says you take, okay, I can write it in general if you want. You have, or maybe I'll take here xk. So this is the formula xk, and you have mu1, mu2 and so on. Let's say mu n. Okay, then what you will do, you will take the product with respect to all mu I belongs to this n, and you take x1 raised to power mu1 plus x2 raised to power mu2 plus up to and so on xk raised to power mu k. Okay, so this is the formula. You expand it for all I, so you will get x1 raised to power mu1 plus up to and so on xk raised to power mu1. With mu1 you expand, and then in multiplication you will get for mu2 also, and then with multiplication you go on till whatever the last is. mu n. So for example, as you asked 3 to 1, so from this we can x1, x2, x3, we can actually calculate it. What does this say? This says you take the product. So product means you expand it for all n. So this is mu1, this is mu2, this is mu3. So for mu1, firstly you will write with mu1. So mu1 is 3. So cube you will take, and then with in product you will get for the second one is a square. Then the last one is 1. So x1 plus x2 plus x3. These are all in multiplication. So this you will get. Is that clear? Is that clear?
Okay.
I can show you in the lecture notes if you want. You can just go through.
Yeah, I understood that.
Okay.
Yeah, I saw it, the lecture notes, but that time I did not
Okay,
understand.
sure, no problem. Yeah, this is the formula. Is that okay? Are there any
Yes,
other
ma'am.
question?
Yes, ma'am.
No? Okay.